All right, welcome back to magnetism. We're talking about domains of an object and how iron, because of the uncanceled spin of the electrons, are already kind of weakly magnetic. If you have unmagnetized iron, notice that the domains are pointing in all directions. If it's become slightly magnetized, they're kind of lining up. And when more and more of them become lined up, it becomes more strongly magnetized. All right, if you were to break it, these small ones, since they're lined up equally like they were before, are both equally strong as the magnet that they were broke off of. All right, and so that's just some things about how the magnetics works. Now, we said before though that magnetism and electricity are kind of like twins. When one happens, it just turns out that it induces or causes the other. Okay, if you have a moving electrical charge, which would be like in an electrical current, okay, you will notice there's going to be an electromagnetic field induced around it. So for example, if here is a wire carrying electric current, as the electricity moves through here, it creates a magnetic field, and you'll see that they all point the same direction. Okay, make a circular magnetic field around this wire. If you reverse the direction, they will change direction. Still point in a circle, but now they will point the north and south will be at opposite ends, and it will flip this way. So depending which direction the current is moving, it will induce a magnetic field, and it will flip the poles of that magnetic field if you switch the direction of the current. And so we see that electricity and magnetism are definitely related. Now, it wasn't long for someone to realize, well, if there's a magnetic field around a wire, okay, so like here we have a wire and we have the magnetic field around it. If we were to coil this wire around over and over again, like a spring, that these circles would overlap in the middle and they would all be pushing the same direction. Okay, and so basically in effect they would be kind of reinforcing each other. And so say you had two loops, then you'd have twice as strong of a field there. Okay, so here we have one wire. You can see the magnetic field around it and the iron filings. Okay, but now we have a loop going through here. You can see how it loops around the wire. But if you put a bunch of loops in a row, a coil basically, then these loops overlap and you see the strong up and down here. Now to make it even stronger, you can put a piece of iron, okay, which is going to line up and form domains all lined up according to this magnetic field, and that will make it even stronger magnetism. Now basically we have what we call an electromagnet, okay, and so basically if you have an electromagnet, it's a magnetic field, usually with a, like I said, piece of metal down the middle of it, and as long as the electric current is flowing through there, it will continue to have this electromagnet. Okay, so these coils with a iron core in the middle of it lines up its electromagnetic domains and makes a very strong electromagnet. All right, the stronger the current, then it makes a stronger magnetic field. If you lessen the current, you lessen the magnetic field. So basically you have a variable magnet. You can adjust the amount of current and then adjust how strong the magnet is. You also can turn the magnet off. If you flip the switch, turn off the electricity, then basically there is no magnet anymore. And this becomes very handy if you've seen the very large electromagnets they use at junkyards, where they pick up the car, usually with the hero or the heroine tied up in the back seat, and it's like, oh, are they going to get out before they get crushed? But then they can pick up the car, and if they just turn off the electricity, then it will drop the car. Okay, we'll leave it to decide someone else to save the hero or heroine out of the back seat before it does that. But basically, if you turn off the electricity, then you've turned off the magnet. So you have a magnet that's variable or can just completely be turned on and off, which gives you an advantage. Okay. These kind of magnets are used in accelerators, which are particle accelerators. You may have heard called atom smashing, where they have underground circular paths where they turn magnets on and off to cause atoms to go faster and faster and faster and faster, and then they finally smash them together or into other things and see what all the little pieces that come flying off the atom. That's how they have researched a lot of the smaller parts of an atom below electron, protons, quarks, and mesons, and some of those kind of things that you may have heard of. Okay, but they use the magnets by turning them on and off to make them go faster and faster and faster around here, and that's the same kind of thing, and it's some type of electromagnet. Now, the problem with these electromagnets is that you have electricity. The more and more electricity you put through, the more and more coils you have here, you have more resistance. And if you have more resistance, then you have more heat. Okay? And so that's what limits how strong. If eventually it starts generating a certain amount of heat, then you may not be able to go farther than that. So the strongest electromagnets, in order to reduce the resistance, take out the iron core in the middle, and they use superconductors at very low temperature. And remember, superconductors at low temperatures have no resistance. We talked about during the electricity chapter. And so basically, you can, if you keep the coils cool enough, you can get extremely high magnetic fields because you don't have the heat building up and limiting what you can do. Okay. And now, the other thing that's interesting with superconductors is that if you take a superconductor at very cold temperatures, superconductors have been found to repel magnetic or expel magnetic fields. Okay, in other words, the magnetic field, instead of being attracted to it and boom and attracted to it, it will push on its magnetic field, will push it away, so it will float above the superconductor. And you can see here there's a superconductor magnet, obviously at very low temperatures, and the magnet here, the magnetic field, is just keeping it right above the surface of that. Okay, the same general principle can be used with what they call maglev trains. Mag for magnetic, lev for levitate. Okay, and basically, if they have superconductors in here and magnets, and since the magnetic field cannot or is expelled by the superconductor, it just floats above the rail. Now, the advantage of this is there's no friction, and if there is no friction, then you don't have the rubbing, you don't have the noise as you would have on a regular train. But without the friction, that's where a lot of the resistance is that you have to overcome. And so these trains can go much, much faster. I believe the record is about 321 miles per hour. In fact, when they go, a lot of the energy that they use is due to overcoming air resistance because they're going at speeds more like an airplane. And airplanes are up in the atmosphere where the air is thinner and there's less resistance or friction, air resistance, and they're down here on the surface, so they have more air resistance. And it's really more a matter of overcoming the air resistance than the friction between them and the surface because there's very little to none. Now, the problem is there's also other problems going at these high speeds. How do you do that safely, speeding up, slowing down? You can't be stopping all the time, obviously, if you're going to try to maintain those high speeds. So there are still problems to be worked out. China, Korea, and Japan all have functioning maglev trains. Also, they can't work on regular rail, so you'd have to have your own rail system built for them and stuff like that. So there are some places that have found it useful, but and there are certainly some advantages to it, but they're fairly costly still, and so they're not found just everywhere. Now, it should be pointed out that magnetic forces and moving charges are acting on each other. If there is no electricity moving through this wire, then it is not going to create a magnetic field, and vice versa. Okay, it's a moving charge. When the charges or electrical current is moving through here, then it's going to be affected and acted on by the magnetic field. If it's not moving, then those charges are not going to be affected. Electrical charges are not going to be affected. Okay. For example, if we have a magnet like this, if we shoot an electron beam, a beam of electrons, since they're moving, they're going to be affected by the magnetic field they're moving by, and it will change their direction. A good thing about this is that the Earth has a magnetic field around us. That's what creates compasses. That's why they're attracted to one line up according to that magnetic field on the surface here. Okay, but that magnetic field also protects us from many moving charges or cosmic rays that come through outer space. And so our magnetic field of the Earth helps to protect us from those. Okay, and we don't think about those much because we're protected from them. We kind of take it for granted. But if there were no magnetic field, all these cosmic rays would enter the atmosphere and cause damage to us and other things, living things on the Earth. Now, as another example of this, for example, if we have these wires looped around, okay, and we have electricity going through them, going through all the wires and coming out here. Okay, if we put a compass needle in beside that, or inside of that, as we turn on the electricity, that will cause or deflect the magnetic needle of the compass, and it will not give the true direction based on that. Okay, now that's not good news for your compass if you're trying to use a compass, but it is good for all the different meters that we use to measure electricity. So we hook up a multimeter or various type of electric meters, we will. As the needle goes through here, the electric field will cause this the piece of metal up here to deflect, and by doing so we can measure how much electricity is going through the current. Okay, so a lot of our meters that we use, these are voltmeters and amp meters, kind of older type, but analog, but you can see that they have this little needle, and basically when you plug it in, the current goes through, it deflects this needle a certain distance, and that measures the amount of current that is going through it. Now, any instrument that is used to deflect a needle and measure electric current, whether it be something like this or one of these here, is called a galvanometer. Okay, a galvanometer. Okay, and so basically a galvanometer is basically just an instrument that detects current. Okay, now we have particular types of galvanometers. If we're measuring voltage coming through, we call it a voltmeter. Not meter, sorry. Sorry, meter. Alright, voltmeter. And if it's measuring the current going through it, then we call it an ammeter. Okay, because it's measuring amps. Alright. However, most of what we will use in this class, and most people, electricians will be using, is what we call a multimeter. Okay, and the multimeter will have usually digital, and you can have a knob on it. We'll use that later, where you can switch it to a certain range of amps, maybe milliamps if you're measuring small amounts, amps if you're measuring larger amounts, voltage, also resistance. So instead of an ohm meter, you would use the multimeter. Also would measure resistance, and usually it has a little section where you can measure if a circuit is complete or not, whether it's conducting electricity or if there's some kind of break in it. And also usually one which really is just a voltmeter part, where you can test batteries to see if they're at full strength or not. But those are galvanometer is just anything that detects electric current. In particular, you can have voltmeters, ammeters. You could also have an ohm meter to measure resistance. But usually nowadays we use a digital multimeter that just has a little dial and allows you to pick which of those you want to measure. Deflection is one reason you have to be careful using a compass. If you're near any electrical things that are wires over that might have a fairly high current, they may have a magnetic field. Also, any large metal objects that might have domains of their own that are enough to cause error in your measurements. Otherwise, you'll end up going the wrong direction. Now, very important thing, electric motors that are running all kinds of things around our house, anything that spins basically, whether it be our fans or our washing machines, our blenders, our blow dryers, whatever. All these things that spin with electric motors are basically caused by this. Okay, as we run a current through this wire loop, it has a magnetic field. Okay, and so say this is south. This one, the magnetic field around it is south, and the one here is north. So the south would be running up to the top to be attracted to the north end of this magnet, and the south end of this loop that has current going through it would be attracted, the north end would be attracted to the south end of the magnet. Now, alternating current means that this switches direction. So once they line up, then this one switches because of alternating current. Now it's south. South and south repel, so it continues. Instead of staying here, it spins it on the other direction, and this one's north and north, so it spins it this direction. By the time they get about halfway around, where timing is very important here obviously, the current switches again. Now this one's back to south, so it goes ahead and is attracted back up to the top. This one is back to north again, it's attracted to the south. And this alternating repelling and attracting is what causes the armature here to spin, which basically gives the motor its ability to spin. And so for all electrical motors, this is a very important characteristic and allows them to work. And we have lots and lots of things that we use that use electric motors. So very important thing there. All right, we'll stop right there and we'll see you next time.